Well, we are now living in the artificial intelligence century. There's many people that think that artificial intelligence will only succeed if we create synthetic intelligence of the type of Commander Data from Star Trek, the type of system that would be better than human beings at every pursuit, and only then will artificial intelligence take over the world. But I'm here to tell you that that is not quite the case. That artificial intelligence is already making great strides in narrow areas where in specific domains to solve specific problems, AI algorithms and techniques and products are already exceeding human potential. And this mass application of AI, where it's good at specific things, but it's being applied broadly, this phenomenon will allow AI to take over the world anyway, whether or not we get AGI anytime soon. But where did this begin? If you think about automation and you think about this whole idea of software doing things that previously human beings used to do, Mark Andreessen very elegantly explained this some years ago, and he said, look, software is eating the world. And in a moment, I'll explain what Mark meant by this. I added recently a corollary to this, which is that not only is software eating the world, but in fact, now AI is eating software. So let's take a look at what that looks like. On the right-hand side here, you have an internal combustion engine. You see all the moving parts. On the left-hand side here, you have a modern electric motor. One of these might be powering a conventional auto vehicle, and the other one might be powering an EV or an electric vehicle. You see that the combustion engine has pistons and a timing belt and a carburetor and spark plugs and a distributor cap and a large number of moving parts. On the other hand, the electric motor has a very small number of parts overall, but an even smaller number of moving parts. So the complexity has diminished. But yet, both these systems perform the same function. In fact, in automotives, they're basically replaceable. So why is it that the older technology requires so much more in terms of parts and mechanics and complexity and interaction, whereas the electric motor requires so much less? The difference is software. A lot of the things that the carburetor used to do in the case of the internal combustion engine is now simply being done by software. A lot of the other functions around timing that belts and pulleys used to do in the old style combustion engine are now being done by software. Software is physically eating the world. You don't require as much complexity if you can take simple mechanical constructs and then integrate them with sophisticated software. So that's a very important trend. But it gets even more fun. How do we write software? On the right hand, you have the perfect programmer sitting down at her terminal without making a single syntax error at a very high rate of speed, typing out all the code that she can possibly type out. And she's trying to get her robot to work. So she imagines every scenario, the if, then, else, the if, then, else, the if, then, else, of what real-world conditions her robot might encounter. But regardless of how long she thinks, or regardless of how deeply invested she is in the success of her project, there's just no way that a human programmer can grasp ahead of time with the complexity of the real world. There just is no way in which we can simulate all of the potential complexities that might occur in a scenario like that. But on the left-hand side, what we have is a very different approach. We have artificial intelligence, in particular, genetic algorithms. These genetic algorithms don't really know what walking means. They don't really know what the robots are made of. They don't know the idea of a joint and so on and so forth. They are just trying things at a very high rate of speed in a somewhat intelligent manner within a virtual simulation. And with this approach, they're being able to evolve programs that provide the ability for any one of these robots to start to move and walk And interestingly, depending on the shape of the robot, whether it looks like an ostrich having boxes thrown at it, or a robot, or several other, a humanoid figure, all of these are being taught to walk not by if-then-else rules, but by AI itself. This is a very powerful idea. Now, why is this happening, and what exactly are these genetic algorithms building? What is the control code that causes these robots to run? Well, this is what it looks like. This is a neural network. And now, neural networks, or if you've heard deep networks, they're inspired by the biological brain, and they are connections of tens of thousands, hundreds of thousands, millions of nodes that are all interconnected, exchanging information between them. There are many types of neural networks, and I won't get into the complexity here, but the really beautiful result about a neural network is that it is, for all practical purposes, a universal function learner. In other words, you can take any kind of data, and if you have sufficient data, and you train a neural network with examples from this data set, a neural network can really learn any function. So it can learn how to play Go, it can learn how to play chess, it can learn how to drive a car, it can learn how to make a robot walk in a reliable way. It's a universal function learner. It's a very powerful result. So now, if only we could build these neural networks very quickly, if only we didn't require groups of PhDs in machine learning and AI to build these and apply them to problems. If we could do that, then we could democratize artificial intelligence. And going back to my earlier point, we could then build a world in which we don't really need commander data, because all of our objects and all of our interactions in our buildings and the doors and the cars and the very irritating electric mopeds on Guadeloupe, all of these things could have AI and maybe develop a sense of propriety. So how would you do that? Well, this is the area of my research. This is what we do. We use genetic algorithms, we use evolutionary computing to automatically evolve deep networks. Whereas, on the one hand, you can be a PhD in machine learning and you could sit down and say, okay, for this problem, I need a convolutional net, and for this other problem, I need a recurrent net, and how many recurrent cells should I apply? Should I use LSTM, long short-term memory, or some other technique? That requires a lot of knowledge. There's very few people in the world that can really, truly advance the state of the art in architectures of that type. But what we've built is a new algorithm that employs the concepts from evolutionary computing and genetics to automatically create hundreds of thousands, millions of diverse candidate networks, and then make them compete with each other. And the beautiful thing about this is that this technique is not focused on any one type of domain. It can solve problems across a large number of domains, and we've actually tried it in the field. So if you were to have a system where AI was in fact building AI, and where you could democratize the application of this technology to so many areas, what could you do? What industries could you revolutionize? How could you change the world? And that too is something that we think about quite frequently. So for one, we are applying this technology to really reimagining the skies of the future. Today, you have thousands of airliners in transit at any given point in time. But the future of the world, the future of aviation, will be made up of millions of autonomous drones of all shapes and sizes, carrying all kinds of payloads and performing all kinds of services, from emergency to package delivery to disaster recovery and so on and so forth. But that world cannot rely on today's ATC or air traffic control. That world cannot rely on human pilots because simply the volumes won't allow that to happen. That world cannot even rely on human maintenance. We won't have as many maintenance technicians as we need to support fleets this large. And this is where artificial intelligence comes in. This is where automated model building comes in, where these automated techniques can evolve controller networks, health management networks, cybersecurity networks for each and every one of these individual assets, these individual drones, these individual environments. This will be a big step forward. But we can't ignore some of the other implications of artificial intelligence also on our world, on relationships between countries, on strategic affairs. Artificial intelligence will be deployed in the field of battle. There are many countries today that are working on technologies that take everything from reinforcement learning and deep learning and apply it to autonomous weapon systems of a variety of types. The public conversation today is that countries are generally hesitant automating a weapon system like this. They talk about a human being on the loop, a human always being able to cancel the decision-making of an autonomous weapon system. But General John Allen, who's a four-star Marine general, and myself, for many years have been researching this area that we call hyperwar, the application of artificial intelligence to increase the speed of warfare, to cut short what we call the OODA loop, the observe, orient, decide, act loop. And when you do that with artificial intelligence, you create such speed in observation, decision-making, and action that you compel your enemy to act in the same way. Or if your enemy does this first, he compels you to act in the same way. And at some point in time, we ask the question, does human latency, does human decision-making in that loop actually become a detriment? These are important, deep questions. And these must be taken up by not only the AI research community, but also by policymakers and governments. How can we have a world in which we know many actors will use AI on the battlefield, but at the same time also have a modicum of legality and ethics and morality? These are challenging questions in the AI century. And then finally, let me tell you about power. But in general, even the current power infrastructure that exists in the world, for example, in the continent of Africa, there are many documented cases that power production capabilities do in fact exist. It's the lack of knowledge and the lack of expertise to keep those running that prevents smooth delivery of power and causes interruptions that then, of course, impede daily life, but they also get in the way of economic prosperity. So how might we use artificial intelligence to solve these problems for Africa and other developing parts of the world, and even perhaps in the developed world, make these operations more efficient? And this is where we work very closely with Mitsubishi Hitachi, which is one of the largest manufacturers of turbines. And we engage with them to ensure that artificial intelligence and the leading turbine technology can combine to build the world's first autonomous power plant. That's quite a vision, an autonomous power plant. You may have heard of dark factories, where robotics and artificial intelligence are able to fulfill the entire workflow of production and delivery. But here we're talking about elements of our infrastructure, power plants, that AI can reliably run. So the world is changing for sure. And as I said early on, artificial intelligence, even in its current state, is advancing so quickly that in fact, even if it were to not reach that threshold, the singularity, or being able to build a sentient robot, or create a commander data, regardless of all of those questions, artificial intelligence is here, and it will be a fundamental driver for this century. So the question for all of you is, how will you use the power of AI to change the world in your areas? Thank you very much.